Hello, everyone. Welcome to today's live broadcast, Improvement of both Legacy and New HPLC Methods with Superficially Porous Particle Columns. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event. We're pleased to bring you this web seminar presented by LCGC and sponsored by MacMod. A company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is smarter chromatography. But you may ask, just what does smarter chromatography mean? It means that when they make a recommendation to you about an HPLC or UHPLC product, it's to partner with you to offer innovative solutions to your complex problems. They use advanced, state-of-the-art analytical software to match their product portfolio with your separation needs. They leverage their 30-plus years of experience in the LC column business, their technical expertise, and their manufacturing network to help you solve your toughest application problems. They provide up-to-date and accurate technical catalogs and reports from industry-leading separation scientists to keep you informed of new technologies. Before we get started today, we have a few housekeeping announcements. First, the webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions by typing them in the Q&A box, which you can find on the right-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of the slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation today, please click on the question mark Help widget in the dock at the bottom of your window. I would now like to introduce today's speaker. We are very pleased to be joined today by Stephanie Schuster. Stephanie Schuster earned her BA at LaSalle University in 1998 and her PhD in 2007 under the guidance of Professor Joe Foley at Drexel University. After graduation, Stephanie spent 9 months at Atlantic Diagnostic Laboratories, a combined clinical and forensic testing laboratory. She joined Advanced Materials Technology, or AMT, in June 2009 as a research scientist working with Dr. Jack Kirkland, providing contributions to the commercial development of products designed specifically for the separation of peptides and proteins. Most recently, as the Applications and Quality Manager, Stephanie has been developing applications that highlight beneficial features for both existing and newly introduced HPLC and UHPLC columns. She's primarily interested in the development of separations and novel materials for chromatographic applications. Stephanie has several peer-reviewed articles and is currently a member of the Executive Board for the Chromatography Forum of the Delaware Valley. Stephanie, thank you for joining us today. Please get us started.
Thank you, Laura, for the introduction, and thanks to all who are joining us today. So I'll be talking about improving both legacy and new HPLC methods with superficially porous particle columns. Here's a brief outline of my talk today. I'll go over the advantages of superficially porous particle, or SPP, columns over fully porous particle, or FPP, columns. From there, we'll talk about method transfer and translation considerations. Then I'll go into USP modernization efforts, including the allowable changes to USP methods, and then we'll get into some case studies going from FPP to SPP columns. Then we'll switch gears and talk a little bit about new method development with superficially porous particle columns. And I'll wrap up with conclusion and summary. So first, I'd like to briefly review superficially porous particles. These are also known as fused core, solid core, or core shell particles. The top left shows a cutaway image of an SPP with a solid silica core in gold and a porous shell in blue and white. In this example, the core is 1.7 microns and the shell is a half micron with 90 angstrom pores. So what we do at AMT is tightly control the shell thickness and pore size, so we're able to vary those and also vary our total particle size. On the bottom, we have focused ion beam images showing the comparison between a fully porous particle, or FPP, compared to the halo SPP particle. And you can clearly see how The cutaway image shows that porous morphology throughout the FPP particle, whereas on the right-hand side for the halo particle, you can see that solid silica core, and then that's surrounded by a porous silica shell. So we have particles that are available in both 2, 2.7, and 5 microns, and I'll show examples of all of those today. So let's go over the advantages of superficially porous particle columns versus FPP columns. First, SPP columns provide faster separations and sharper, more efficient peaks compared to FPP columns without the need for higher pressure or extra operator training. And what we're referring to there is comparisons versus sub-2 micron particles. SPP columns have about a half to one-third the back pressure of sub-2 micron FPP columns. And what that does is it enables use of legacy HPLC instruments with 400 to 600 bar limits. It also permits faster flow rates, and what that translates to is increased throughput. SPP columns use 2 micron inlet frits that are less subject to pluggage than the 0.2 or 0.5 micron frits needed with sub-2 micron columns. So here I have some Van Deemter comparisons of SPP versus FPP particles. If you direct your attention to the middle of the right-hand side, you have the Van Deemter equation, where H is the height equivalent to theoretical plate, A is the eddy diffusion term, which is 30 to 40% smaller for the fused core particle columns. B is the longitudinal diffusion term, which is 25 to 30% smaller. C is the resistance to mass transfer term, and mu is the mobile phase linear velocity. So if you direct your attention to the plot, what we have is plate height, or H, plotted on the y-axis, and that's followed by mobile phase velocity plotted on the x-axis. The trace with open triangles is the curve for 2.7 micron fused core particles, and you can see that it's flat at high linear velocities, which means that a faster flow rate may be used with minimal loss in resolution. So in this case, the smaller the plate height, the higher the efficiency or theoretical plates. And look at the huge difference between the 2.7 micron fused core trace compared to the 5 and the 3.5 micron totally porous particle traces. This is where we have increased efficiency, and you can also see how those 5 and 3 micron traces start to increase in their slope as you get to the higher mobile phase velocities. And what that means is when you try to run those columns at faster flow rates, you may start to lose resolution, and that could enable you not to use as fast flow rates and increase your throughput. Now, compared to the sub-2 micron totally porous particle column, we have about similar efficiencies, but if you're looking at the back pressure, like I said before, it would be 1/2 to 1/3 the back pressure with the 2.7 micron fused core column compared to the 1.8 totally porous or fully porous particle column. The 30% smaller A term is due to the more uniformly packed column bed with the fused core particle columns. The 30% smaller B term is due to the presence of the particle's solid core. So what you have is a smaller diffusion path for that fused core particle morphology. And the combination of those is what leads to the higher efficiencies. So now let's talk about the difference between method transfer versus method translation. So method transfer is when you move a method from one column brand and particle size to another, or when you implement a method in a different lab, different company, or a different country. Method translation is when you move a method from one particle size and or column geometry to another with the same column brand. And it's also when you move the same column geometry and particle size to a different instrument brand. So in that case, you would have to consider differences in delay volume and dispersion. And we'll talk a little more about those as we get further into the webinar. So typical scenarios include transferring an HPLC method to a UHPLC column and system, and that's going from an FPP or SPP column to a UHPLC SPP column. Translating a UHPLC method to an HPLC column and system. So, for example, going from the R&D lab to the QC environment, and then direct implementation of an existing method. So in that case, only extra column volume, dispersion, delay volume, and the system maximum pressure would be considered. So what kinds of questions do you have to ask yourself before you decide to do a method transfer or method translation? First off, what is the goal of transferring or translating the method? Are you looking for increased speed or improved resolution or maybe increased sensitivity? So we've talked about different particle morphologies, but we also need to consider the instrument parameters. So for instance, can the new instrument handle the pressure that the proposed new column will generate? And that would be when you're going from, say, a 5 or a 3 micron to a 2 micron SPP column. Can you meet or exceed the original column's efficiency using the new instrument? So what we're talking about there is specifically about dispersion. Does the new instrument have low enough extra column dispersion to allow the required efficiency, or can the system be optimized to minimize extra column dispersion? And I'll show some examples of how to optimize systems as we get further along. Can the new instrument deliver the correct column temperature to match that of the original instrument? So how do the set point temperatures compare versus actual temperatures for the instruments? So in order to answer all these questions, you need to be able to predict pressure, predict efficiency, measure extra column dispersion, and measure the gradient dwell volume or delay volume in the case of gradient methods. So we have some important method and instrumental parameters to consider for both method transfer and translation. For isocratic methods, you need to consider the maximum instrument pressure. So the practical maximum operating pressure is usually 75 to 80% of the instrument maximum. You don't want to be running right at the instrument max because that will wear down your seals pretty quickly. Extra column volume, including the tubing, both the ID and length, and whether you have the same IDs throughout or different IDs can really affect your extra column volume. So what you want to do is make sure you have homogeneous ID columns throughout your sample flow path. The other thing that you need to consider is both the flow cell volume and the path length, the injection volume, and the injector type, whether you have a flow-through needle versus a loop fill. And I'll talk about that a little bit later as we go. For extra column dispersion, that's measured from the injector through the column into the detector and including the detector. So the less dispersion, the better resolution and sensitivity you'll have. And this is a function of flow rate. It also is dependent upon the data rate and response time and the instrument type. So in general, HPLC systems have more dispersion than UHPLC systems. For column heater type and calibration, you need to consider whether you had a forced air or block contact heater, heat tape wrap, etc. And you also have to think about the actual temperature versus the set point when you're transferring methods. And finally, frictional heating. So effects on efficiency, peak width, and selectivity can all influence your transfer. For gradient methods, we have to consider everything that we've just went over for isocratic methods, except there's less impact on efficiency and peak capacity from the pre-column tubing dispersion. And for gradient methods, we need to think about the delay volume or dwell volume in terms of whether we have high pressure mixing, which would be influenced by the mixer volume, or low pressure mixing, which generally gives higher dwell volumes. And this is often a function of back pressure, which is proportional to the column length, flow rate, and 1 over the particle size. So some examples of instrument optimization. What we really want to do is minimize the volumes. So all the connections from the column to the flow cell are important, but the most important one is the one that goes from the outlet of your column to the flow cell. But in general, I would recommend that you minimize as much extra column tubing as you can. And also you can use a smaller volume pre-column heat exchanger. They can be as small as 1.6 microliters. For data acquisition, you would want that to be appropriate to your peak width. So you need to increase the detector time constant to monitor fast eluting peaks. And the data rate should be at least 20 Hz for best results. So I have some examples of the effect of data acquisition rate on efficiency. So in the first chromatogram, you can see we used a data acquisition rate of 2.5 Hz. And what we're measuring is the efficiency of the last peak, which is naphthalene. So we start out with sort of broad-looking peaks at 2.5 Hz and plates of 11,100. Just by doubling the data acquisition rate to 5 Hz gives a huge increase in plates, and you can see they go up more than double to 25,100. Going from 5 to 10 Hz, you still see a fairly significant increase in plates of 41.8%, and the plates go up to 35,600. And then finally at 20 Hz, you're up to 38,200 plates with 7.3% increase over what you had seen at 10 Hz. So if you notice the peak that's eluting near the middle of the chromatogram, look how much sharper and taller it is as you go to the higher data acquisition rates. So this is really key for superficially porous particle columns because the volumes that you see are very small and narrow, and you want to be able to accurately measure those peak shapes. So this is why the data acquisition rate is so important. Continuing on with instrument optimization, you need to consider the type of pumps and mixing. So quaternary versus binary pumps, you would typically see more extra column volume with quaternary pump versus a binary pump. And then in terms of comparing a convergence block versus a mixer, we would generally recommend a mixer because those volumes can be modified based on what kinds of analysis you're trying to do. For the volume of the flow cell, we recommend using a smaller volume, and these can be as small as 250 nanoliters up to 5 microliters. The injection type, so if the needle is in flow, that would add volume but improve the carryover, versus a fixed loop, which would minimize the volume, but carryover could be problematic depending on the compound. So you would need to evaluate that on a case-by-case basis. For injection volume, you would use the smallest practical injection volume, keeping in mind the precision of the autosampler. So you don't want to inject too little that would affect your signal to noise, and you don't want to inject too little that you would be way out of the precision of your autosampler. And then in terms of sample solvent, you want to keep the volume small as practical if you're using a stronger solvent than your starting mobile phase, and then you want to match it. Generally, you want to match the sample solvent or have it weaker for improved sensitivity, LOD, and LOQ. And then if you have an injector program, you can use Poise, which would be with an aqueous or a weak chaser. So here's an example of the effect of reducing the flow cell and the tubing volume. So for this peak, which is 1-chloro-4-nitrobenzene, we observed 8,563 plates, and this is with a 10 microliter flow cell and the standard ID tubing. Now just going from reducing the post-column tubing to 100 microns by 300 millimeters and switching to a 2.6 microliter flow cell, we see a 30% increase in plates just by reducing that excess volume in the system. So there, depending on what HPLC or UHPL system you're using, you can really see some big advantages just by going to a smaller flow cell and shorter tubing with smaller IDs. So now let's talk about USP modernization efforts. The USP is in the process of modernizing existing monographs to use current UHPLC columns. And this has been going on since 2011. It's a combined effort between USP and several partners in industry, and there are hundreds of methods that could be modernized, so that's why it's been taking so long since 2011. And there's also a harmonization effort among the USP, EP, and JP. So now I'd like to review the allowable changes to methods according to USP Chapter 621 guidelines. So changes right now to USP methods are only allowed for isocratic separations. I do know that there are harmonization efforts, like I said, between USP, the European Pharmacopoeia, and the Japanese Pharmacopoeia, and they're working to allow changes to gradient methods. But they all need to agree before those changes would be allowed. So that the agreeing part hasn't happened yet. So right now we're only able to change isocratic methods, and for considering particle size and or the length of the column, the ratio of the column length to the particle size, dP, is the same or in the range between -25 to 50% of the prescribed L to dP ratio. Or you could do, for particle size adjustments to superficially porous particles, other combinations of L and dP can be used, provided that the number of theoretical plates is within -25 to 50% relative to the prescribed column. The bonded phase may not be changed. Temperature may be adjusted plus or minus 10 degrees C, and the flow rate may be adjusted plus or minus 50%. So now I'd like to go over some case studies where we have examples of legacy FPP separations transferred to SPP columns. This first example is an isocratic NSAID separation going from a 5-micron fully porous particle column to a 5-micron SPP column. And what we've done here is we've kept the conditions the same and the column diameter and ID the same. The only difference is that we've used a superficially porous halo column versus the original FPP column. So the FPP column results are on the bottom in black, and the SPP results are in blue. So you can notice that the separation on the halo column is about half the separation time on the FPP column, and more than 60% higher efficiency is observed on the halo column. So not only are you getting your separation done faster, but you're also seeing an improvement in the efficiency. So everybody wants more time and more throughput, so a simple one-for-one swap like this doesn't really require a lot of, I guess I would say a whole lot of effort. And this next example is a case study using 11 steroids under gradient conditions, going from a 5 micron FPP column to a 5 micron SPP column. So the top trace is using the 5 micron FPP column in 4.6 by 250 millimeter dimension. And what you can see is coelution of peaks 7 and 8, and then coelution of peaks 10 and 11, highlighted in green and orange. But when you go to the halo column, you can see that we've kept the particle size the same at 5 micron, but we've gone to a smaller ID and a shorter column. So we can do the separation 2 times faster with better resolution of those peaks highlighted in green and orange, and also we're using 3 times less solvent. So not only are we able to do the separation faster, but we're also able to see some money savings in terms of solvent, both in the use and disposal. This example shows the isocratic fat-soluble vitamin separation going from 3 micron FPP to 2.7 micron SPP. And in this case, again, we've used the exact same conditions and the exact same column dimensions, 4.6 by 150. So what we see with the top trace in black with the halo C30 column is sharper peaks and increased resolution compared to the FPP C30 column in 3 microns. So if the plates are more than double on peak 2, so you only have 11,400 plates on the FPP column compared to 24,800 plates on the halo C30 column. In addition, the resolution between peaks 3 and 4 is 1.6 on the halo column compared to only 0.87 on the FPP column. And again, this is just an easy one-for-one swap. We didn't change any column dimension or condition. They're run under the same conditions. Here we're showing an optimized fused core separation that yields up to 6-fold increase in throughput. So this chromatogram that's shown here is run on an HPLC in standard configuration with extra column volume of approximately 35 microliters. It's using a large volume flow cell at 14 microliters and the standard response time, and then the standard length and ID of tubing. So with this, you're getting the separation done in 12 minutes compared to when you switch to the halo SPP column. Not only are you using a shorter column in 4.6 by 100 millimeter dimension, but you're also able to use a faster flow rate. So you can see the total runtime is reduced to 2 minutes, so that gives you your 6-fold increase in throughput. And you're able to maintain the resolution between peaks 2 and 3 and also maintain the plates. So with this HPLC in ultra-low extra column volume configuration, the ECV is approximately 10 microliters. We're using a smaller volume flow cell at 5 microliters and the same response time, but we've reduced the length and ID of the tubing. This case study looks at an isocratic phenolic acid separation going from 5 micron FPP to 2 micron SPP. So the top chromatogram is run on a 5 micron 4.6 by 250 millimeter FPP column, and you can see the total runtime is about 25 minutes. When we go to the 2.1 by 100 millimeter 2 micron halo SPP column, we're able to get the separation complete in 15 minutes. And also we see an increase in plates up to 19,500. So you might be thinking, oh, well, she didn't really go that much faster. It's only not even 2 times faster, but look how much solvent you're saving. That's 5 times less solvent. Can really add up if you're running this assay multiple times. And then finally, taking the same separation or the same components that were looked at from the previous slide, now we're using gradient conditions. So what you can see is on the top chromatogram, which is the 5 micron FPP column, that separation is complete in 15 minutes, and we're not getting baseline resolution on the first pair of peaks. Whereas on the halo column, we're able to increase or decrease the total runtime to 3.75 minutes, and then also increase the resolution to 1.94 or baseline. So not only is the SPP method 4 times faster, but in this case you're using 12 times less solvent. So now I'd like to switch gears and talk about new HPLC method development with SPP columns. So for new method development, that depends on the complexity of the sample. The gradient approach is best when you don't know how many components you have. Single screening gradient on one phase can give you a quick look at the sample, so that's one strategy you can use. And then a use of multiple phases and conditions can help you select the best combos to move forward for optimization. So here I have a list of the halo phases available for reverse phase, HPLC, and UHPLC. For C18 and C8, these are used for mixes of acids, bases, and neutrals, and many people, as you know, start with C18 for their method development. For phenylhexyl and biphenyl, these are used for aromatic compounds and can show some selectivity differences compared to your alkyl phases. ESCN is used for very hydrophobic compounds and aromatic compounds as well. And then FPP and C30, which C30 is one of our newest phases, these are used for isomers since they are shape selective. And then finally, RP-amide and AQC18 are used for polar compounds and can be used under 100% aqueous mobile phase conditions. So in this case, what we did was we took a contrived, complex, blindly prepared mixture of 13 to 20 compounds, and these could have been acids, bases, or they were a mix of acids, bases, and neutrals. So the strategy was to screen 4 different halo phases, and we used C18, phenylhexyl, cyano, and RP-amide. We used 2 different organic modifiers, including methanol and acetonitrile, and then we looked at different pHs with LCMS-compatible buffers. So we looked at ammonium formate at pH 2.8 and 3.8, and ammonium acetate at pH 4.8 and 5.8. And the idea was to identify 1 or more possible combinations for further improvement or optimization. And you can see our run conditions are listed on the right-hand side of the screen. And what we did was we had measured the delay volume using DryLab. So that was 0.74 mils. And then what we did for our gradient was to use a 1-minute hold at 2% B. So using our flow rate of 0.6 mils per minute, that gave us an additional volume of 0.6 mils, and that gave us an effective delay volume of 1.34 milliliters. And then here in the bottom, you can see our total runtime for each of these screens was 17.5 minutes. So using that in combination with the 4 different bonded phases 2 organic modifiers, 4 pHs, and 2 injections under each of those conditions gives a total of 64 runs, which was a total time of 18.7 hours. And if you were running these screens overnight, that would only take about less than a week to get through all the experiments. So there are 2 approaches that you can take. One is if you're just looking at keeping the conditions constant and just swapping out different bonded phases. So in this example, we have the comparison of C18 in the top left, cyanophase in the bottom left, phenylhexyl in the top right, and rpamide in the bottom right-hand side. And what you can see are some different selectivities for the different bonded phases. So this is one way to go through the screening and look at the results. And another way is to evaluate pH. So in this example, what we did was we held the bonded phase constant and we varied the pH of the buffer. So in the top left, you have the conditions that were run at pH 2.8 with acetonitrile. Then the bottom left is C18 with pH 4.8 buffer. The top right is C18 with pH 3.8 buffer. And the bottom right is C18 with pH 5.8. So you can see the selectivity of the later eluting peaks seems to do better at lower pH compared to higher pH. And then I want to point out that you should also consider organic modifiers, because a lot of people may just think that acetonitrile is always going to give the best answer. But sometimes you can use methanol or mixes of methanol and acetonitrile to improve selectivity. So in this example, what you have are some of the best screening results that we had with all of the conditions that we had screened. So the top left shows the cyanophase run with methanol and pH 3.8 buffer. The bottom left shows phenylhexyl under acetonitrile conditions with pH 2.8. And then the top right shows phenylhexyl with acetonitrile run at pH 3.8. And then the bottom right shows phenylhexyl with acetonitrile run under pH 5.8. And what we decided to do was optimize the separation using the phenylhexyl column at pH 5.8. So here you have the predicted separation from 2 runs at 10 and 30 minutes using dry lab 4. And that's compared to the bottom trace, which is the actual experimental results of the phenylhexyl column using a 2 to 32% B gradient in 10.46 minutes. And you can see we were able to separate all the compounds and some impurities under these conditions. And next I have an application example where we evaluated 5 halo phases with 12 different beta blockers. And in this case, we used 2 1x100 millimeter columns and a gradient with acetonitrile and 0.1% TFA. So here's the comparison with the 5 different halo phases, and the separations marked with stars will be the ones that we would then go on to further optimize. And you can see there are some coelutions with all the bonded phases except for the biphenyl phase. So that was one that we were particularly interested in, and that one would go on to further optimization. So the interesting thing about the comparison between the halo C18 separation and the halo biphenyl separation is how much the peaks move around. So for instance, you have coelution of peaks 8 and 9 on the halo column, halo C18 column, and you're able to resolve those peaks just by going to the halo bifunnel phase. The other interesting thing is that you have a elution order switch with peaks 7 and 8 going from the halo C18 to the halo bifunnel, and then finally another elution order switch going from halo for peaks 10 and 11. These reverse and are better resolved on the halo bifunnel phase. So in addition to our particle technology, the available phase chemistries enable faster and more comprehensive method development. So in summary and conclusions, I hope I've convinced you that the use of fuse core columns to modernize legacy methods enables faster separations, equivalent or better efficiencies, and increased resolution. The use of different column selectivities with different organic modifiers and pHs can be an effective approach for ensuring all sample components can be seen and acceptable combinations of column modifier and pH can be found. For moderately complex and very complex samples, it can be effective to screen different stationary phase types, organic modifiers, and pHs to identify a promising combination for further refinement or optimization. And this is for related substance methods, multiple active ingredient drug products, or OTCs, impurity profiles, forensic analyses, and environmental samples. Short, efficient, narrow ID fuse core columns allow faster screening of various combinations of conditions and faster answers to UHPLC challenges. And I have some acknowledgments. I'd like to thank Joe DiStefano, Tim Langlois, and Barry Boyes for their suggestions and encouragement. Stephanie Rosenberg for all of her help and encouragement, and Connor McHale, Robert Moran, and Will Miles for running some of the experiments. And then at MacMod Analytical, I'd like to thank Alex Nassa, Tom Wagey, and Jeff Faden for their suggestions and input. So that concludes our presentation, and now I'd like to hand it back to you, Laura.
Thank you very much, Stephanie, for that excellent presentation. In a few moments, we'll start the question and answer period. But before we do that, I would just like to ask everyone in the audience to participate in 2 brief polling questions. Please click directly on your screen to enter your answers. So here's the first question. Would you be interested in a personal consultation on your method development of your analytes using halo columns? Yes or no? So once again, click directly on your screen to answer the question. And that question is, would you be interested in a personal consultation on your method development of your analytes using halo columns? Yes or no? Fantastic. Thank you. Let's now move to the second question. And it's waiting for that to come on my screen there. Okay. So here's the second question. And again, click directly on the screen to enter your answers. From which manufacturer do you currently source your columns for small molecule separations? Waters, Agilent, Phenomenex, Toso Bioscience, Merck Millipore, Thermo Fisher Scientific. So once again, from which manufacturer do you currently source your columns for small molecule separations? Waters, Agilent, Phenomenex, Toso Bioscience, Merck Millipore, or Thermo Fisher Scientific? Excellent. Well, thank you, everyone, for participating in our 2 polls. It is now time to move to the question and answer period. As a reminder, if you'd like to submit a question, you can do that by typing it in the Q&A box, which you can find on the right-hand side of your presentation window. All right, so let's find the first question here and get started. Okay, so here we go, Stephanie. How does sample loading capacity compare between superficially porous particles and fully porous particle columns?
Okay, that's a great question. We get that question a lot, actually. So it really depends on what analyte you're looking at. So in general, for neutral compounds, I'd say you get about 80% the sample loading compared to on SPP columns versus FPP columns. But it really depends on what conditions you're using and the identity of your particular analyte. So of course, everyone knows that superficially porous particles, by their particle design, have less surface area. But I like to tell people that they're still competitive in terms of the sample loading, and we have papers on that too.
Excellent, thank you. What if the selectivity is different on the corresponding halo column compared to the one I try to transfer a method from?
Okay, so if the selectivity is different, you might see an improvement in the separation, or you might need to slightly adjust your experimental conditions, including the mobile phase composition and temperature, to achieve comparable selectivity with the halo column.
So here's another one. How will I know that the halo column I choose to shorten or speed up a method with will work with my instrument's pressure limit?
Oh, that's a good question. So what you can do is estimate the back pressure from your halo column by calculation if you know both the flow rate, the column porosity, the temperature, and the mobile phase viscosity, and the column permeability. So there are tables of mobile phase viscosity depending on the temperature, and those parameters aren't too hard to get.
Great. Here's a related question. What about ID? How do I know if the internal diameter I choose for the halo column will work with my instrument?
So first, you would need to know the dispersion of your instrument, and that would need to be measured. If you have an instrument with low dispersion, then you'd be able to use 2.1, 3.0, or 4.6 millimeter ID columns without having to worry about loss of performance. But if you have something, a legacy HPLC with a lot of dispersion, then you're not able to optimize it, you might not want to use a 2.1 millimeter ID column.
How do you decide what flow rate to use?
Oh, to decide what flow rate, you need to consider your pressure limits of the instrument and the ID of the column that you're using. So for 2.1 millimeter ID SPP columns, we recommend using anywhere between 0.25 and 0.6 mils per minute. If it's a 3 millimeter ID, we would recommend 0.5 to 1.2 milliliters per minute. And for a 4.6 millimeter, I would recommend using 1.2 to 2.8 milliliters per minute.
So here's another one. How do I know, sorry a minute. How do I know where I'll get the best performance in terms of linear velocity?
Okay, so you'll get the best performance at the optimum linear velocity, and you can do a simple experiment with your own analyte under isocratic conditions and vary the flow rate to determine which conditions give you the best efficiency, and you'd want to operate there.
Do you have any recommended method transfer tools?
Yes, there are several sources of free method transfer tools, and I could send you the information if you provide your contact information.
Excellent. How do I estimate the pressure I'll get?
So, like I said before, what you can do is, if you know the flow rate, column porosity, temperature, mobile phase viscosity, and the column permeability, you can estimate that pressure by calculation.
Excellent. All right, well, I think we'll wrap up. Stephanie, thank you so much for your excellent talk today and for answering all those questions.
Oh, you're welcome. Thank you very much.
I also want to thank everyone in the audience for attending and participating in today's event. And I'd like to thank our sponsor, MacMod, for making today's webcast possible. You'll receive an email from LCGC alerting you when this webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.